Hello everyone and welcome to 11th lectures of Digital Image Processing of Remote Sensing Data course. And this one we are going to discuss about how multispectral analysis, especially involving several bands, that means multivariate analysis, can be done in digital image processing. So in this we will be going through the scatter plot, two-dimensional plot, band ratio analysis, principal component analysis, and decorrelation stretch. So these are the topics for this. First, what is basically multivariate image statistics, because we know that the most of the remote sensing data is acquired in multispectral form. That means lot of bands data is coming, and therefore we need to analyze that data. So it is often concerned with the measurement of how much radiant flux is reflected or emitted in case of thermal infrared from an object in more than one band, because this is the main thing, is not a single band analysis where a histogram is more than sufficient and stretching options are also simple. But when we go for multi-bands or multivariate analysis, things becomes little complicated. So it is useful to compute multivariate statistical measures such as covariance and correlation among several bands to determine how the measurements covary. This is required because if there are say 7 or 8 bands in a one scanner or sensor, then many of these bands might be highly correlated to each other, and so that whenever we are going for some color combinations or composites, we need to have those images which are different than each other, and therefore the bands which are correlated to each other may be dropped in color composites. So this kind of analysis will allow us to understand and select the relevant bands. It includes this multivariate analysis, as I have mentioned earlier, band ratioing techniques, which we will discuss, several limitations and advantages with band ratio, principal component analysis, very popular one, PCA, feature selection, classification and accuracy assessment. So mainly image transformation, and that is multivariate. That image transformation typically involves the manipulation of multiple bands of data, whether from a single multispectral image or from 2 or more images of the same area acquired at different times. That is multitemporal data, image data. So that can also be analyzed in this way, and either way the image transformation generate new images from 2 or more sources which highlight particular features or properties of interest better than the original input image. In case of single band images, most of the things which we have been doing through the LOTs, and maybe in some cases new images may not be generated, but in a multivariate analysis these things are there. So first, very simple multivariate analysis involving more than one band may be the image division or band division. So the most common transforms applied to image data, that is image division, on pixel by pixel basis carried out the following operations. For example, band 1 divided by band 2. So a new band is generated and resultant data then rescaled to fill the range of display, because if you divide the number of the range of pixel values might reduce, and therefore you want to rescale to the display range that is between 0 to 255 in most of the cases. So this is very much required. In most of these multivariate analysis, this rescaling is the last step which has to be done every time. And this image division is applicable, commonly also called a band ratio, and very popular technique which we will see. So mathematically, basically if you look that VVIJR equal to VVIJK divided by VVIJL, and in this one VVIJK, that is the brightness value at the location line I, pixel L, J and K band of imagery. That means the band 1 in this case k equal to 1 we can consider. So band 1 and each pixel, basically this division will be made pixel by pixel. So that is why locations of both pixels are given in all these two bands K and L, and output band is the ratio image which is denoted here as R. So this L is the brightness value of the same location in band L. The corresponding pixel will be divided. This one has to remember, and the ratio value at the same location, that is the in case of output image, and in denominator is 0. If B end up, then denominator BV is made 1, because there might be a situation when the band L, that means maybe band 2, when we create the ratio, the value becomes infinite, so we rescaled to 1. And what are the applications of ratio? Major one is to remove the shadow effects induced by the rugged topography, and basically our ultimate aim in all these image processing techniques to improve the image interpretation. So our images becomes much better for interpretation. So this is what the undesirable effects on recorded radiances, that is the variable illumination caused by the variations in the topography. In daytime, if you are working in a hilly region, then one slope of the valley might be illuminated, the other one may be in the shadow, and this kind of affects this differential solar illuminations can cause difficulties while making image interpretations. So if we employ band ratio techniques, then these effects can be minimized, that is the effects of topography due to the differential solar illuminations. Sometimes differences in BB, that is band values from identical surface materials, are caused by topographic slope and aspect, shadows or seasonal changes. So all these, the orientation of slope and with reference to the position of the sun will play a major role here, and these conditions hamper the ability of interpreter, as I have already mentioned, to correctly identify surface materials or land use in a remote sensing, and ultimately it will affect our interpretation. And ratio transformations can be used to reduce the effect of such environmental conditions which are present in a hilly regions especially. Here is the example is given here, that one side of the slope is illuminated on this left side, whereas in the right side of the slope is in dark, and therefore like in digital numbers of different features which are given here, like for the slope which is in band A might be having a pixel value of 48, in case of band B 50, but when we create a ratio it becomes 0.96. Of course the pixel value has to be in ratio image, has to be integer value, so it is rescaled later on to make a rescale to integer. Same like in case of shadow, in band A or band 1 it is just 18, whereas in band B it is 19. So again ratio is getting quite close as in case of sunlight and shadow, and therefore the effect of shadow is getting reduced. Another example, this is this was from deciduous trees, forest or vegetation. Then you are having examples of coniferous trees, that here in case of sunlit slope, in case band 1 it is 31 pixel value, in case of band 2 or band B it is 45, so ratio comes 0.69, and in case of shadow again 11 and 16 ratio comes 0.69. So when we will make the integers values, then these values are coming very close, whereas in original bands these values were at very far, and this is what the advantage. We are removing the effects of shadow which has been caused due to the presence of rugged topography. So even if we are having same cover type, no problem, and if you are having different cover types, then depending on the which features are there, or which land cover are there, that will reduce the effects of topography. Radiance at shadow is only 50% of radiance of sunlight, as in many cases we are seeing here generally, and the ratio nearly identical, whereas the end result becomes identical, and hence removal of topographic effects. Now, applications of shadows may be that ratios may provide unique information not available in any single band, because two bands information are being used, and ratio, a simple mathematical technique, and ratio discriminate subtle spectral variations, and it contains aspect of shape and spectral reflectance curve of different earth surface covers can be brought out of by ratio. Ratios are independent of absolute pixel values, and ratios can be used to generate false color composites by combining three monochromatic ratio data sets. That means if you are having many bands, you can create ratios of two different bands having three outputs. So, three ratio outputs. These three ratio outputs can be combined and can be created a color composite. So, it's a multi-bands ratio. So, instead of involving just three bands in this ratio color composites, you would be involving 6 bands and less effects of topography, and therefore the image interpretation may become very reliable. So, ratio clearly portray the variations of slopes of spectral reflectance curves between two bands involved. Here is the example here, like in case of Landsat TM, you know that they are covering first in the visible part, then band 4 is in the near infrared part, then band 5 is the middle infrared part, and then band 7 is in far, basically far infrared. Now band 6 is not mentioned because band 6 is thermal, so that has not been considered in this particular slide. Now different objects which are present on the earth, their spectral curves would be different in different bands. This is what you are seeing. So if I create a ratio between say band 4 and band 3, then I am not only removing the topographic effects, but I am involving two bands, and the same time, because here the vegetation is making major change here, so in this spectral curve, and therefore these bands, this kind of band ratioing will help us. Similarly, wherever the major changes are there, in case of vegetation, in case of dry soil or wet soil or water bodies, turbid water bodies and so on, clear lake water bodies, they all behave differently, and ratios can exploit that one, and you can have a better output image for reliable interpretations, image interpretations. For example, which bands to ratio example. This is what in the previous figure I was mentioning, that the healthy vegetation reflects strongly in near infrared because of high chlorophyll content, and the spectrum while absorbing strongly in the visible red. As you can see here, that healthy vegetation will have a high reflectance in near infrared in case of Landsat TM band 4, whereas in red band of Landsat TM, that is in band 3, you do not have much reflection, and this is what that the healthy vegetation reflects strongly in near infrared portions of a spectrum while absorbing strongly in the visible red, and because of this sharp curve we can exploit. So other surfaces types such as soil and water, so near equal reflectance in both near infrared and red portions. It is not necessary that all objects or all kind of features which are present on the earth will behave differently. Vegetation behaves differently, water body, dry soil, wet soil, they all are having different spectral curves. So we need to understand the spectral curves, and accordingly we should choose the band and then create the band ratio. Thus, the ratio image of near infrared divided by red would result in ratio much greater than 1 for vegetation, and ratios around 1 for soil and water. And that is why I was mentioning that where the curve has there is a sharp change in the curve, those two adjacent bends will give you much better results. Thus the discrimination of vegetation from other surface covers types is significantly enhanced in such ratio outputs. And also we may be better able to identify areas of unhealthy or stressed vegetation suffering from lack of water or maybe disease or something. These by implying this ratio you can clearly identify the health of the vegetation, which show low near infrared reflectance. There is a shift then, if healthy vegetation less chlorophyll content, the curve will shift towards the red and the ratio would be lower than the healthy green vegetation. So employing such a bend ratio technique, even in case of vegetated areas, the health of vegetation can also be assessed easily. And this is an example of real example that this is infrared channel. These are from IRS list 3 and this is the red channel. And as you can see that this is the vegetated area which is coming dark in red channel, whereas in infrared definitely it will have a better illuminated part or have high brightness compared to red part. But when we create a ratio, then all the features which are present become much more clear. Second thing is you will observe that the effect of topography, especially in this hill part which is the Shivaliks in this here, they will that has been reduced, and you see this image which is more or less quite representing a flat terrain, but we know that it is not flat, but for interpretation it might be better for certain applications. So that is a big advantage, that the discrimination power of the output image becomes much higher, much reliable compared to individual bands if I would have been using. So that's the advantage of band ratioing. When the band ratio of two bands, as have been mentioned, removes much of the effect of illumination in analysis of spectral differences, and this is possible because the composition between two geologic units, for example limestone which is grey white and in red bed which is the red, determine the ratio of any two bands, whereas the illumination determines magnitude of the DN received by the satellites. And here is the example, this is the sun and the energy is coming, it is getting reflected. So if you are having this is the illuminated part, so this is the red band, this is the limestone, and they are giving different reflection, as you can see 46, 23, 23 and likewise. And however the areas which are having haze or atmospheric distortions or having this because of relay scattering, these numbers from these rocks or reflection from these rocks has reduced significantly, roughly half. So in the however in the areas with significant haze, the performance of ratio is much improved by removing the haze produced by relay scattering in the atmosphere. And therefore band ratioing, when we find that there is a haze, then we can employ again band ratioing to improve our images. So the product image, the ratio image, will have the less effects of scattering because that is causing the haze. So relay scattering effects can also be minimized. And this is the example here, that this is the band 1. Blue radiation shows strong topography effects, where the ratio of band 3 by band 2 removes much of the effect of illumination and yield differences of rock. And here you cannot identify different rocks very clearly, and the effect of topography is very much dominating, but here the effect of topography has reduced, whereas the discrimination between two rocks or many rocks have increased. So that's the advantage of band ratioing. Another example about the color composites. So these are the two band ratios, 5 by 2 and 7 by 4 involving Landsat TM data, and here that all these three are in RGB, that is the color composite of band ratios. So 3 by 2 which goes in red channel, 5 by 2 goes in green channel, 7 by 4 goes in blue channel. And when we get a output image. Now you compare this output image either with 5 by 2 single or 7 by 4 which are involved here, but you don't get that kind of discrimination power of different features which are present then in this color composite of band ratios. So it is a very good tool in image processing to exploit the maximum variations which are present in different bands and can and create a new product. Here band 2, band 3, band 5 and band 4 and 7. So 2, 3, 4, 5 and 7. 5 bands characteristics, variations have been incorporated in this color composite. And normally we can only incorporate about 3 in a standard false color composite. So that is why it is giving much better results. Now little advanced band ratioing techniques, and that we end up just not by dividing but making more different combinations or bringing little more arithmetic in it, and that is very popular one is called Normalized Difference Vegetation Index or NDVI, and it is for using relatively coarse resolution data like NOAA AVHRR or MODIS data. At global scale NDVI maps are being used. So we can assess that what is happening to the vegetation cover globally. And in this one, the near infrared band is subtracted by red band, and this whole is divided by near infrared plus red band. And that it will, what NDVI will do, it will bring highlight the health of vegetation. So where increasing in red show stress vegetation, and VNIR, that is very infrared band, shows chlorophyll, and that is why these two bands are involved in this normalized difference vegetation index. Here is the example, like this is the healthy vegetation. On right side you are seeing the vegetation which is not having much chlorophyll. So here in infrared the reflection is coming about 50% and in visible just 8%. But when we go for a dry leaves or vegetation which is suffering from stress, maybe lack of water or some disease, then the near infrared reflection has reduced here by roughly 20%, and whereas visible reflection has increased very significantly from 8 to 30. And if we see the ratios, then see this is a healthy vegetation ratio is 0.72, whereas in case of not healthy vegetation, vegetation under distress is just 1.4. So that's the advantage, that you can assess in a vegetated area the vegetation which is suffering from stress, and the discrimination between healthy and a vegetation suffering from stress will be enhanced, as we can see here. And these are the examples of at continental scale or country scale, UK and Northern Ireland and some part of Europe as here. So this is the NDVI of June 2003, this is the NDVI of October 2003. You can see that how this NDVI has increased or decreased. So in October, because now this is the onset of winter and you are having very less NDVI value, but in case of June, which is you are having a full of greenery and NDVI is touching even up to 1. So that's the you can assess that how vegetation cover at because generally we employ coarse resolution data, so at country scale or continental scale, and this vegetation conditions can be assessed. Now further to this there is a further analysis which is called PCA or principal component analysis, where we use the scatter plot, two-dimensional histogram. We have already discussed when we discuss histogram and scatter plots. So we will just directly go for this, and I will explain on this graphics that we plot band 1 and band 2 like this. Now if they are correlated like this, this is showing that they are very much correlated. So then this origin is shifted in the center and this rotation is there. So this becomes, so the origin instead of here is shifted here, and the principal component 1, this is aligned with the maximum variations which are present between these two bands, and the next one is the PC2, which is perpendicular to PC1. And now think that if you are having multi-band data or multispectral data, so you can graphically I can represent mainly 3 components, PC1, PC2, PC3, but with using digital image processing softwares, we can go for many not only 3 but maybe 4, 5, 6 depending what you are trying to achieve. So here only I am showing 2. So because of band correlation, which you are seeing here, that one sees in band 1 is not so much different from what we see on the band 2. And as per linear algebra, we are making eigenvectors where the eigenvalues contain the contribution of each band to the principal component. And this is what we see here, that there are the 6 principal components of band 1, 2, 5 and 7 of Landsat TM. 6 is missing because 6 is thermal channel. So that is not involved in the analysis. And this is what you are seeing, that principal component 1 will always have the maximum variations. And the principal component which is last in this case is 6, which will have maximum noise, and as you can see here. So all noise which is having not much relation with any bends will go in principal component 6 in this particular example, and maximum variations which are present in the image in these images of 6 channels, 6 bands, they are all has been accumulated basically, if I can use this word, with principal component 1. So principal component, the component 1 image will have maximum variations, the last one will have maximum noise, nothing else. And now one more step is also possible, because now I know that this band is there, the other principal components are highly decorrelated, I mean they are not correlated. So I can also make principal composites of principal components. So I can use principal component 1, 2, 3 and assign say red, green, blue in this thing, and I can create a color composite of principal component. And such output images not only involving 5 or 6 bands, in this case, in this example 6 bands, but when we create a color composite, they are creating much more better images for of course for reliable interpretations. This is how the generally statistics which you will get, that band 1 here, band 2, band 3 and band basically here in this is shown as band 6, but band 7 basically, and this is correlation matrix and this is correlation eigen vectors are there. So band 1 definitely it is 100% correlated, so 1 is there, and similarly you can see that how they are correlated. Band 1 to band 2 is 0.9, so it's a very high correlation, and therefore principal component analysis would be much useful in such cases. Now the next step in principal component analysis is decorrelation stretch, which is again based on the principal component analysis. Like example is shown here, that band 1 and band 2 scatter plot is showing a highly correlated data, and what we can do, we can shift the origin as in case of principal component analysis, and then stretch along these axes to occupy the full range which is available for display. And by this we are decorrelating each component, within each component, and at the end if we see this scatter plot, we are occupying a very large area which was not possible with the normal thing. So this band 1, band 2 is correlated, highly correlated is there, whereas band 4, band 7 are less correlated. So in this is the situation, and if we plot and see this cube here, this is the original RGB, this is how the pixel values are distributed. When we go for decorrelation stretch, DCS, in RGB color space, they are occupying a very large area or a space within that color cube, which we have been discussing also. And this is another color combination where if I go, then we are occupying much more area which is available within the color cube. And HSY, the hue, saturation and yellow color space, then we are occupying little less. So this decorrelation stretch and in RGB combinations many times will give you much better results with full of colored images. An example here is that this is simple RGB image, but when the principal component and then we did the decorrelation of different components, principal component or PCs, then made a color composite, this is what the result is. And see that the quality of discrimination. Here I can discriminate different rocks, different ground features comparatively very easily than on simple RGB image. So this is the advantage of going for multivariate analysis in digital image processing. And this brings to the end of this lecture. Thank you very much.